Welcome to Fermilab. I know some of you have been here many times. For some of you, it's your first time. We're very happy that you could come out and join us. I'm Katie Yerkowitz. I'm the communication director here. And my job is to introduce a representative from the Department of Energy. As some of you may know, Fermilab is a lab that is funded by the U.S. Department of Energy and operated by a contractor, Fermi Research Alliance. So Mike Weiss is our site office manager from the Department of Energy, and he's going to say something.
All right. Thank you, Katie. And I want to also add my welcome from the Department of Energy, Office of Science, the High Energy Physics Program in Washington, D.C. Welcome to the largest physical Office of Science laboratory in the entire country. Welcome to the premier and only particle physics laboratory, national laboratory in the country. And it's incredible honor to be one of the partners. In order to make up a national laboratory, you have to have the federal government support, and the Department of Energy is the one that's providing the support here. And an incredible partnership with the contractor and the team that they brought in to be the ones that drive the mission forward. So I just want to say it's been an honor working with Pierre. I'm going to introduce him as the laboratory director, Pierre Adoni. Dr. Adoni, incredible 8-year distinguished service here at the laboratory, and I want to just introduce Pierre to the group. So, Pierre.
Thank you, Mike. Thank you for coming. I really appreciate you wanting to look at the future of Fermilab. I also have met many of you through various activities at the laboratory and your support through all the years that I've had here. So it's also my opportunity to thank you. I'm going to be going back to California in the middle of July, and so I've had 8 years here that have been quite marvelous for me. And one of the remarkable things, I think, of this region is how much support we have from the local community, and that's you. And I come before Fermilab from a lab where our relations with the community were, I would say, very rocky, and we never had the kind of all-out support that we feel we have from our community here. So I very much appreciate that, and the fact that you're here also tells me of the interest that people have in our laboratory. Now, we have gone through a very critical transition, because when I came, I knew during this tenure I would have to shut down the Tevatron. And that's not something that we should be very sad about. It had a fantastic career, set up things for future machines, and it really is in a sequence of events that our field as a global field goes through. When we built the Tevatron, Europeans shut down their machine to come work here because we had higher energies. And it was a much more powerful machine. And now we have shut down our machine here, and we have a vital program over there. So our field is very global, very broad-looking. And instead of continuing the Tevatron, we had to make a transition to a set of new programs. And that's what I'm going to talk about. Because one of the problems we have with some folks that I meet in the community, not so much around here, but certainly in other places, is, gee, you shut down the Tevatron, Fermilab is about to shut down. And I had this personal experience coming back from abroad one day with the person that stamps the passport. I live in the lab. I have one of the houses here in the lab. So he looked at the address and said, oh, I'm so sorry for you. You're going to lose your house. And, you know, but positive thing is he knew about Fermilab. The not so positive thing is they thought, gee, the lab is closing down. Well, far from closing down. Now, you heard from Mike that we're the particle physics lab for the country. Now, what has happened? Because there used to be lots of particle physics labs. Almost any laboratory in the system started as a particle physics lab. But as projects have grown, there has been a consolidation of facilities at this laboratory. And so for Illinois, it's a very sweet deal, because about half the program, half the funding for particle physics is associated with the program of Fermilab. Now, it's a big country, lots of universities, lots of labs, so typically a laboratory gets 10% of the program in the country. We get 50% of this particular program. And because we are uniquely the laboratory that can build the big accelerator facilities, if we can convince the country to build the next accelerator facility, we are not in a fight with other laboratories about where it should get built. It gets built here. So in many ways, if you want to build a new light source, a new anything, there's going to be a competition, all sorts of labs get involved, and so on and so forth. That's not the case for us. So for Illinois and the support of Illinois legislators is very, very important. But for Illinois, supporting particle physics as a whole automatically supports Fermilab. Now, so we recently went through and looked at our mission and vision statements, and it says Fermilab is America's particle physics lab. I explained that. And what is our mission? Well, our mission is to inspire the world and enable its scientists to figure out what's going on in nature. At a very deep level, matter, energy, space and time, they're all connected. And we have found with the Higgs, for example, that we have a field that permeates everything. Without it, there would be no atoms, no chemistry, no nothing. That field is in a funny place where the universe is all metastable. We worried when we looked at the mass of the Higgs that, gee whiz, how long is the universe going to last? Well, it's a long time. You don't have to worry about it. So the mission, then, what is it that we do about that is to drive discovery in particle physics by building and operating world-leading accelerator and detector facilities. And we have those. Even after the Tevatron, we have the second largest accelerator complex in the world. We perform pioneering research with our global partners. Essentially, every experiment that we do here brings many countries. And we transform technologies for both our own science, but when we do that, we also transform technology for industry. And I will say a few more words about that as we go on. One of the remarkable intellectual constructions of the last century was to figure out the standard model of particle physics. And we use machines, accelerators like the Tevatron, and detectors, and this detector is called Minerva, it's a neutrino detector. And we have done many, many experiments over the years, and we can put it all together in a very simple graph. And it's remarkable. Mendeleev's table is a hell of a lot bigger than this. This is really tiny. So there are 6 quarks in 3 families or 3 columns. There are the leptons, which are the electron that you know very well, but then its heavier cousins, and then the neutrinos, which continue to be a big puzzle and very strange for us. And these particles transform into each other through forces, and there are only 4 forces that transform the particles. The weak force that is connected with these 2 heavy particles, the photon, which is connected with electromagnetism, and the gluon that glues together the nucleus and gives us the nuclear force. And we had a mystery. What was giving mass to the particles? And we have now just found the Higgs boson. Now, to understand the Higgs boson is, through mathematical equations and all of that, it's something we're not going to do in the next 20 minutes. But I want to give you a way of thinking about this. If, for example, we were like fish in water, and we were trying to figure out the laws of motion. The laws of motion for us, the classical laws of motion, is F is equal to ma. The acceleration is proportional to the force. Well, if we were in water, we wouldn't find that. It would be very complicated. It would have to do with the friction of the water, what the velocity that the particle was traveling in the water. And so the laws that we would come up with is very complicated. But if we were smart enough to figure out we were in water, we could all of a sudden figure out a very simple set of equations, which we call Newton's equations, that are very simple. Well, that happens with the Higgs. The world that we look at has all sorts of masses for all of these particles. It turns out, if we're smart enough, we can figure out that that's due to the Higgs field and put a much simpler set of equations where all the basic masses of the particles are 0. So we have figured out this, and at the same time that we have this beautiful construction, we're full of mystery. We don't know what dark matter is. We don't know what dark energy is. We don't know why the world is dominated by matter and not antimatter. We don't understand neutrinos hardly at all, and so we pursue this to try to see how all this really comes together. So while we have explained lots of experiments that we've done with accelerators, we look at nature and it's full of mystery still for us, and that's what drives us. Now, Fermilab, we have about a little bit over 1,700 employees. We, of course, mostly live around this area. We have about 2,300 visiting scientists from all over the world. I said we're the largest site for the Office of Science. Office of Science has 10 labs. We're the largest lab. Not in budget. I wish it were in budget. In area, which means cost in terms of taking the site and the roads and everything else. Interestingly, for the community, about 25,000 people, including student groups, about 20,000 of those are students, took public tours of Fermilab in 2012. And we get wonderful letters from teachers and students who come here and are inspired by what we do. In terms of job impacts, we have, of course, the jobs at the lab, but there is a multiplication effect of what our visitors and our own people impact the economy. And when you add it all up, it's close to 5,000 jobs and an impact on the economy of over $600 million. So it's a big thing. And as I mentioned before, we work with everybody. We have divided our field in 3 frontiers. A intensity frontier where we do neutrinos and use beams of very high intensity, the energy frontier where we use colliders like the Tevatron or the Large Hadron Collider, and the cosmic frontier. And in each one of these frontiers we work with a whole bunch of partners. So as I mentioned before, it is really a global field, and Fermilab plays a very special role in that global picture. For more than 25 years we operated the Tevatron, and that was the most powerful particle collider in the world. It made many discoveries, including the top quark, and we shut it down in 2011 due to the startup of the Large Hadron Collider. And so we're going to be working over there, and we have a massive program. When you are in the atrium, you see the control room. We actually take shifts on the detectors over there. They're not happening now because the machine is shut down for repairs for the next 2 years. But when it's operating, we can monitor the data collection and actually take the data from here. And here is Fermilab. So what we have done, and this is a bit of a misleading picture, but we like to show it that way because it makes our remaining ring look as big as the Tevatron. Well, it isn't quite as big, but from this perspective, since it's closer to us, it looks big. It is nonetheless a very large synchrotron in the world, not the most energetic, but certainly the one with the greatest number of particles, greatest power. And we drive experiments for neutrinos out to Minnesota, and we propose to build a long baseline neutrino experiment all the way to South Dakota, and I'll talk about that. We just broke ground yesterday on what we call a muon campus, where we'll have 2 world-class muon experiments. We have a test beam facility that has more than 250 users to test instrumentation. We have big fixed target beam lines. We have an advanced accelerator, test accelerator that is aimed at the future of the laboratory and new technologies. And we propose to build something we call Project X that would multiply the flux, the number of particles at Fermilab by a factor of 100 and put us way out there at the leading edge of the intensity frontier. So we have lots of things to do as the laboratory moves forward. So one of these experiments is using an existing beamline. It's called the NOVA experiment. Quite a remarkable experiment. What you see here is one block of this experiment. The block consists of extrusions, plastic extrusions that we fill with scintillating oil. Each one of these blocks weighs about 200 tons empty, and then when we fill it, it's 500 tons, and then we have to build 28 of these blocks. So you can imagine the scale of this. At the end, we have 14,000 tons. So that's a huge experiment. And the beauty of this experiment is that every piece of this detector is sensitive to the particles. The way we have been able to achieve large masses in the past was to put steel plates and detectors. Steel plate and detectors alternating. And of course, if something happens in the steel plate, we're blind. In this detector, we're not blind anywhere. The 14,000 tons are completely active, and we can see the neutrinos coming from Fermilab interacting in this block. It's in a very nice building that already earned a National Recognition Award. It's up in Minnesota, and we are at Fermilab we have an ear detector because the physics is done by comparing an ear with a far detector, and the caverns are just being finished, and we're building an ear detector on site. So this is a marvelous project. It's sort of the next step in neutrino physics. I mentioned the Muon campus. We have 2 experiments. And these experiments are aimed at trying to tell us whether the vacuum behaves with only the particles that we know, or there are other things going on. Our vacuum is not really a vacuum. It's seething with particles appearing and disappearing. And if only the particles that we know are doing that, then we know precisely what the anomalous magnetic moment, G-2 of the muon, should be, and we know the conversion of a muon into an electron should never happen. But if there is anything else there that we haven't figured out yet, then we're going to see effects, and this will be essentially revolutionary because it will point us to what lies behind at energies perhaps even higher than what the Large Hadron Collider can reach. So the experiment for the anomalous magnetic moment of the muon is called G-2. An earlier version was run at Brookhaven, so we are recycling a lot of components. We're recycling this big magnet, 700 tons. We're bringing the steel, and that's easy. You can disassemble the steel and put it in trucks. But the thing that is not easy is the coils. Because the coils, superconducting coils, we cannot break apart. They would be destroying them. We would have to rebuild them here. We don't want to do that. So we're going to transport them, and it's quite a challenge. Because as you see this device, it takes essentially 4 lanes, and you have to take them from Brookhaven in Long Island to a barge, take that barge all the way south and up the Mississippi to the Des Plaines River, and then debark in Lamont, and then put it on trucks and bring it on site. So it's going to be quite an adventure. It will happen later this fall, and you can see it already, because the marvelous rendering programs allow you to actually see things before they happen. And you have to squint your eyes to see that it's a simulation and not the real thing. So here is coming into the road. It obviously is over this lane and 2 more lanes and the other lane, and that's the object. So when this time comes, you're going to see pictures in the newspaper. We're trying to figure out whether we have liability insurance so we can have a party along the way and all of that kind of good stuff. But it's going to be quite an impressive thing, and it will be a marvelous experiment. Another experiment, which is a precursor of what we want to do, the big experiment that we call the long baseline neutrino experiment, is an experiment that is taking place on site. We're building the detector here. It's called a time projection chamber. We built a building here to house the detector, and we have received the cryostat. This detector will go inside this cryostat. This cryostat will go inside that building and is placed in the neutrino beam that now runs to other experiments. The big one, and the one that we're fighting to get in place, and which would be by far the best experiment in the world, and some that would be very revealing of what neutrinos are really like, is an experiment in which we shoot neutrinos from Fermilab all the way to the Sanford lab, which is deep in a mine, the Homestake mine, which was an old gold mine. The detector will be deep underground at almost 5,000 feet. This is about 800 miles apart. So when you have to shoot a beam from here to there and it goes through the earth like that, locally the horizon is flat like this, so you're going down like this. So you have to build a beam that goes into the earth, because the earth is going to be round. And that's what we have to do. So in order to protect the aquifer and not go too deep, then we are going to build a hill. It's a 52-foot hill. It's about, I think, half the size of this building here. We have to consider whether we'll put a ski slope there. And then there is a decay pipe and a target hole and all of that, and that produces the beam of the beam. Sometimes people think that in order to have a beam of neutrinos, we have to have a big pipe from here to South Dakota, but no. There are no need of pipe for neutrinos. The neutrinos go through the Earth as if it weren't there, almost. And in fact, the fact that the Earth is there makes very interesting changes in the way the neutrinos change into each other, and that's part of the physics that we're after. Now, I mentioned that we do experiments at very, very high energies with colliders like the Tevatron or the LHC. We also do experiments with neutrinos and very rare processes like muons, which we call the intensity frontier. There is a third frontier that again gives us many of the mysteries that we are trying to figure out. And that's what we call the cosmic frontier. So we look outside and we see all sorts of things happening in nature. And because we're arrogant enough to think we really have figured out how things work with the quarks and the leptons and the neutrinos and the four forces and all of that, everything should fit into that picture. If we really have gotten it right, it should, you know, the fundamental laws should explain everything that we see. And when we see things that we just don't see how to fit into this model. And that's what propels us forward. For example, we study dark energy and dark matter. What we have discovered in the last couple of decades is that us, the sun, the stars, the atoms, are but a very small part of what's out there. And what's out there is mostly something we don't see, except for the fact that it's pulling or pushing the objects that we do see, the atoms that we see. And so if it's pulling, it's like gravity. If it's pushing, is what we call dark energy. And so we do that by really studying the motion of objects in the universe, their brightness, supernovas, clustering, the microwave background radiation, and all of that to figure out what is this property that space has that leads us not to contract as we would under gravity, but actually the universe is accelerating outwards. We went to measure that, thinking when we started that, gee, you know, it's a lot of mass. We know that mass produces gravity. It ought to pull things in. And we went to measure how fast it was pushing things in. In other words, slowing the expansion of the universe. And the big surprise is, hey, you're totally wrong. I mean, you're really out. This thing isn't decelerating at all. It's actually accelerating. So this is now probably the biggest mystery we have. The other one is that the galaxies are spinning and rotating much faster than they would if they only had the mass that we can see, the bright stars. There is something there much more massive, so that it, like the force that is exerting is much higher. It's as if when you have a stone, if you spin it faster, the force and the tension is higher. The same thing is happening here. Everything is moving much too fast. And so we don't understand that. So there are other mysteries. So one of the things that we have done is finish a camera that we have installed in Cerro Tololo in Chile. You see here the big dome. It's in the Atacama Desert, up the mountains, and is the biggest camera in the world in the sense of pixels. It has a very wide field of view, and it's got 0.5 gigapixel. And we are about to start a survey where we'll look at millions of galaxies to try to understand how they cluster and how they interact with each other, trying to understand what dark energy is. Now, dark matter is equally mysterious, and some of the favorite theories tell you that dark matter is composed of particles. And so we are hunting for those particles. And because it's dark and it doesn't seem to interact with anything and it's only gravitational, it means that it's interacting very weakly. And if it's interacting very weakly, you can have lots of dark matter particles. This room is full of dark matter particles. They just go through you like the neutrinos do. And so the way to detect these particles is to go way, way down, where you can shield yourself from everything that is going on, all the cosmic rays and everything else, and then basically listen for a bump in the night or a scintillation or a bubble that tells you something came in that shouldn't have come in, but we see it because it interacted with the nucleus. So there are many techniques to do this. This is a cryogenic detector that works at very much less than 1 degree Kelvin, almost absolute zero. So these detectors are totally quiescent, and they react to a bang from a potential dark matter particle. This is the same thing in a bubble chamber, where the recoil, when the dark matter particle, putative dark matter particle, hits the nucleus, it would create a bubble, and there shouldn't be any bubbles down there. So we use all of these techniques to try to figure out what dark matter is. And the lab is, at this moment, leading in what is the world leader experiment, the Dark Energy Survey for dark energy. And we have 3 entries into doing the next generation dark matter experiments with very promising techniques. I mentioned that we work in the Large Hadron Collider. The largest group of physicists, of researchers, actually is working, of Fermilab, is working in the compact muon spectrometer, CMS, at CERN. And as I mentioned, we have this remote operations center where we can run shifts. And it's a center really not just for Fermilab. We support 50 US universities, are part of the collaboration in CMS. And you can go to Geneva and with the present exchange bust your budget with buying Swiss francs so you can eat. Or you can come to Fermilab and have a much, get twice as much work done and make your money go a lot longer if you're a research group at a university. The key is to have a critical mass of technical people here, so that if you're sitting at a university in the US, you think twice of whether you want to fly to Switzerland or come here. And so we try to make it so that the universities have terrific support here. If you have a student, they very quickly can come up to speed on running this very complex, how many million lines of code? There are probably several tens of millions of lines of code that people have to get on top of to run and get physics out. This is a very exciting project, the Illinois Accelerator Research Center. We were funded by the state to build this very nice building that you see. If you came in through the Batavia Road, you'll see the building going up. And we were very fortunate. What we had proposed to the state was a building that cost twice as much, and of course we got half the money. But then what we decided to do is to build the office component, lecture hall, and some space with that funding, but attach it to the collider detector hall that now was essentially housing a detector that wasn't running, the CDF detector. So we basically recover the full scope of this, of what we had originally proposed. And the idea here is to bring industries and universities working together to develop the accelerators of the future. There are about 30,000 accelerators being used commercially, and they affect medicine, they affect lots of industrial processes. There are lots of ideas about how they might be used for cleaning flue gases, for treating wastewater, for doing inspections of cargo containers and all of that. And the key to that is to build them inexpensively, to have high intensity. And so we have already quite a bit of interest of companies that want to come and work with the lab in trying to develop these applications. And for us as a field, it's important because often we are asked the question, gee, okay, you discover the Higgs, so what? What are you going to do for me tomorrow? What economic impact are you going to have? Well, in the process of discovering a Higgs, we've done lots of things having connected with detectors and electronics and all of that, and those are spin-offs, but we don't directly have a piece of our mission, or did not have a piece of our mission, to help the country more broadly in the development of accelerators. That has come to pass. The Office of High Energy Physics that we depend on now has been declared a steward for accelerator technology for the country, and we are the Office of High Energy Physics National Laboratory. So we expect to have a big role in that, and of course that helps already. We have one company that has relocated or opened up a branch from Canada to work with us on accelerators and located to Batavia, and there are other local companies that are working with us. There are many, many opportunities here. In particle physics, if you look historically, it's done an amazing thing. The World Wide Web came from particle physics. Physicists were the first globalized science field where people have different platforms, have to communicate. across countries and continents, and so at CERN initially, but in the national labs here at SLAC and Fermilab, we had the first websites. As I mentioned, there are applications of accelerators in industry, making materials, in medicine, in the MRI machines were really possible because we industrialized the production of superconductor when we built a Tevatron. And many of the things that have come after us, when we developed accelerators, for example, the light sources like the APS that now have the tremendous usage in material science, in understanding the structure of proteins that are used in medicine, rational drug design, and all that comes from accelerators. But initially, those accelerators weren't developed for those purposes. Those accelerators were developed for particle physics, and then particle physicists found out, oh, gee whiz, these things, what a headache. We produce a lot of synchrotron radiation that is actually stealing the energy of our machines, but somebody else can use those photons that come out of a synchrotron. And so that's the way that many of these other activities that are so productive in industry come, but they have their roots in particle physics. The long-term plan, I mentioned this project called Project X that does many things for us. We would first build a 1 giga-electron volt LINAC, superconducting LINAC. It's a very special machine. It has tremendous power. It has the right timing structure. We've never had it for protons before. And so we would build it at 1 GeV and use it for the muon campus and as an injector to the booster for the rest of the program. But then we would extend it and have a high-intensity campus for muons, kaons, all sorts of experiments here, very powerful, 3 megawatts. And then we would steal 10% of the beam, accelerate it, and that would then come into the main injector and ultimately go to the long baseline neutrino experiment. And the beauty of Project X, the way we have conceived it, is that because of the timing structure, it can deliver different timing structures to different experiments simultaneously. And so all of this stuff would be working all at once, all the experiments. We wouldn't have to give some time to one experiment, a little bit of time to another experiment, and so on and so forth, like it often happens. The whole complex would have almost an excess, or let me call it an excess of protons. We could run everything simultaneously. The proton economics that we now struggle with to deliver enough protons to each of the experiments essentially goes away. So then what's the other part of the long-range plan? We want to have a master plan so that we think about our site so that we maintain its many positive attributes while we're trying to do all these different experiments. And the site, as Mike mentioned, is terrific. Is 6,800 acres, is the largest site. There are future machines, muon colliders and whatnot that we think would fit in the site, that would occupy almost the entire site. But that's in the long-range future. In the meantime, we need to understand, as we put facilities in various places, how they harmonize together. And so we have been working for the last year and a half in a master plan where we try to think ahead of time, what are the facilities that we need, what are the visual corridors, what is the campus of the 21st century with all the advances in communication and all that. Can we bring more people together to the central campus? So this is just one example where you're in Wilson Hall. This area here is a parking lot now. It would become a plaza. We would have an office area adjacent to the building, but with parking behind it. This corridor would become what we call a collision hall because it would have a lot of traffic connecting to the main floor of Wilson Hall, with conference centers and facilities for running the machines, the control rooms right there, so that visitors would come in and see things immediately and be immediate in the middle of the activities of the building. I'm very excited about this. Of course, it will take us many years to accomplish this, but if we have a vision, every time we get an opportunity to build a building and move things, then we have this vision of where we are headed, and I think that's going to be very important. We have to fit the landscape with the needs for people, with the needs of experiments that are often dictated by the geometry of machines or where the beams come out. And so it's actually intellectually a very interesting exercise. We do a lot of educational outreach. I mentioned that we have 20,000 students almost that participate in activities at Fermilab. We also go and affect 20,000 students outside. We have about 200 volunteers that go and give talks to classes across the neighborhood. There are about over 300 teachers that attend workshops at Fermilab every year, and about 140 teachers that use our resource center. We have STEM career fairs where you see lots of kids running around with kiosks, talking to people. It's actually lovely to see. We run Saturday morning physics, where it brings about 300 high school students to learn about physics. And we, of course, have the Letterman Science Center that hosts 3,000 visitors a year. And we curate the site. We really feel incredibly fortunate to have a site like this one. About 1,100 acres are restored prairie. We also lease the land for farming. I volunteer, as many others in the community, to go gather seeds. We have all sorts of interesting prairie plants, and the seeds are valuable. We use them on site, but we also trade with other prairie centers so that we can curate the prairie, and that's a very nice activity. We do that seed collection several times. Another thing that we do that I just did last Saturday is we invite the families of the people who had the farms here, because when Fermilab was established in the late 60s, there were about 56 farms that were expropriated and people were displaced. And but we've kept track and we've learned about the families, and so once a year we do a big potluck and they all come with, I don't know, 4 or 5 generations. I have stopped counting. I bring the little kids to see what their great-grandparents were doing in farming, and if we have not maintained one of their barns, or their neighbor's barn is better maintained than their barn, I hear about it. And it's quite interesting, because the first time I joined a meeting like that, I said, you know, if they took I have a farm in California, I have a vineyard, if somebody took that thing away from me, boy, I would resent it for centuries, you know, if I was around. It turns out people love it. And they love it, I think, because they realize that if Fermilab weren't here, this would have become shopping malls and suburbia like much of the surrounding. And so the fact that they can come in and show them how the land was, and we have the farmhouses around that they still recognize, they have old pictures that they can show their kids, is something very sweet for them. And so they appreciate that very much. But that's just part of our taking care of the site and make it available to our neighbors. So I think we have made this transition. I think we are sailing steadily through very turbulent waters. It's difficult to raise the funding that we need to put all this program in place. I think we have a great program. I think it's a brilliant future for the lab. I'm very excited about it. And I think that with a little bit of luck, as the economy recovers, as the federal, congressional, agency turbulence subsides and maybe gets straightened out at some point, then I think we're going to do very well. But it may take us a little bit of time. Whenever I talk about the plan, I say we have to keep our eyes in the long range and have a clear vision of what we want to do, and understand that we're going to have up and downs and turbulence and so on. But if we keep a steady course to where we want to get, eventually we get there. And that's what I expect will happen here. Questions?